Yeah, they were like down to like 12 a.m. Like everyone was like, are we going or not? Band decided and cheerleaders were like, we're done at this point.
Yeah, everybody was like.
Chapter 6 is thermochemistry. So we're back into actual chemistry, back into, when we did chemistry last chapter was kind of physics heavy. This is back into chemistry. There's some physics too.
Yeah, when's it get real?
Not yet. Not yet.
When it gets real, it goes
Not yet.
Wait,
You'll know.
Wait,
Oh, we'll know.
Yes.
do we do any OChem in here?
No organic chemistry in this class. It is not on the AP Chem test. But if you guys would like to do some of that aptitude test, we could.
That actually be really
Any GMO chemistry?
All right. Energy. How would you define energy in another word, chemistry-wise?
Capacity to do work.
Yeah, true. That's more.
Energy, so.
When we're talking about energy in chemistry, where is energy? What?
Source of
Where is the source of most energy in chemistry?
Heat?
Heat. Yeah, I was thinking heat. Sorry, I didn't hear that. But remember, heat does not equal temperature. So I'm just doing a couple misconceptions. Heat and temperature are completely different. Would you have heat? All right, drop your pencil. All right, put your hands together. Is there heat there?
Yeah.
Yes.
No.
My hands are just warm.
Well, how does heat flow?
Is there heat transfer?
Heat flows from hot to cold. If your hands are the same temperature, the question is there really heat, right? So in order for there to be technical heat, what's the transfer of energy, right? Has to be different temperatures. Now if you put your hands together, right, rub them together, and then you put them on your desk, definite heat transfer there, all right?
Feel that.
And the heat is flowing from your hand to the desk. So does cold exist?
Yeah. Wait, no.
Cold doesn't technically
It's just the
exist.
absence
It's
of
just the absence of heat.
Nothing cold.
All right? So heat is not temperature because we know that temperature is defined as what? Average kinetic energy. So temperature is the average kinetic energy of a substance, which takes us to the first law of thermodynamics. Thermodynamics, and I believe you guys all know this. The first law of thermodynamics is energy cannot what? Yes. Energy cannot be created or destroyed. Energy cannot be created or destroyed, comma. What can it do?
Only transferred.
It can only change forms. It can only change forms. So the way I like to define heat, this is my definition, heat is more the direction of the flow of energy. Heat is the direction of the flow of energy. That's how I like to define heat. So if two things are the exact same temperature, I like to say there's really no heat there, right? There is heat, yes, we know that by definition. But if there's no directional change, it's really hard to say that there is actually heat. Okay? So, this next part's big, all right? This is very, 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 very important. And that's as big, that doesn't say BI6. Okay? That's big.
It looks ABI6 is what it looks.
So, for heat, anybody know what letter we use for heat?
I would like for it to be H.
It's not H. Aaron?
Triangle. Isn't it the triangle?
Q.
One.
Q. All right? The big thing about heat is the following. Negative Q lost. So the heat that's lost has to equal the heat gained. So if something loses heat, we assume the same amount of heat will be gained. And if something is losing heat, what do we call that in chemistry? If it's giving off heat, that is exothermic. So the exothermic reaction should be equal to the endothermic reaction. So if something is gaining heat or taking heat in, it's endothermic. I think of heat as entering. If something is exothermic, heat is exiting. Heat is exiting. How does something that is exothermic feel to you? Hot. Something that's endothermic to you would feel cold. And if something is exothermic, it has a negative sign. And if something is endothermic, it has a positive sign. A positive and a negative sign. Okay. You guys good so far? Okay. So we look at what we like to say systems. So we have systems plus the surroundings. So we look at these two things. We look at systems and we look at surroundings. Surroundings is what, well, yeah, I would say surroundings is what the system, we look at what the system does to the surroundings. So surroundings is what is happening because of the system. So the system, is it making the surroundings hotter? Is it making them colder? Is it taking heat away from those surroundings? Is it putting heat into those surroundings? Those are the two things we look at. There's three types of systems. There are three systems. Number one is an open system. Number one is an open system. Open system is matter and energy move. Matter and energy move. So an example of an open system would be my room right now. My room is an open system. As people are entering and exiting, there's matter moving and there's energy moving. That's an open system. Number two is a closed system. Number two is a closed system. In a closed system, guess what doesn't move? Matter doesn't. So a closed system, energy moves, but not matter. Energy moves, but not matter. That's a closed system. And type 3 is the hardest one to make. This is an isolated system, which is also known as a Yeti cooler. Everyone here have a Yeti? Yetis are incredible. I used one this weekend. I filled it up with ice Friday morning, and as of Saturday night, basically none had melted. Like, that's how efficient a Yeti cooler is. Now, did some of the ice melt? Yes, it did. It's not perfect. In order to have like an isolated system, you'd almost have to have, it's hard to get an isolated system.
Okay.
All right? Because an isolated system is no energy or matter is moving. So neither is moving. That would be very difficult to get. And if you're going to have something better than a Yeti, guess what we're going to have to be continually putting in to make it work? More energy, right? So it's almost like a refrigerator at that point. So those are the three types of systems. You'll see it written like this. Delta E, I'm going to tell you what these equal, equals Q plus W. Delta E equals Q plus W. So here come the deltas. Lots of deltas now. All right, they're all starting to come. Delta E is the change in overall energy. So this is the change in overall energy. Q, we know, is heat. And W is going to be work. You got it. W is going to be work. If delta E is positive, then work was done on the system. Work was done on the system. If delta E is negative, the system do work. Sorry. The system does work. All right? Very similar to endothermic and exothermic. So positive, work is being done on me. Negative means I am doing work on something else for delta E. These are pretty easy. These are mostly plug and chug problems. We'll talk more about those in a little bit. Questions so far? Because I need to turn my page. Can I turn my page? Okay, turn it. Okay, so now we're going to talk about what we're going to be doing in the lab tomorrow, which is specific heat. Did you guys talk about specific heat in physics ever?
We did. I don't remember.
Okay, so our definition in chemistry is the heat. What just happened there? required, the heat required, I have like ink on my pinky, and I write like a 3-year-old, so
You can't spell pinky without inky.
you're right. The heat required to raise, sorry about the blur, 1 gram of substance, 1 gram of substance by 1 degree Celsius. Or I could also say 1 what?
Kelvin.
Kelvin, it's the same thing. All right, so you'll see that either way. So the specific heat of a substance is the heat required to raise 1 gram of that substance 1 degree Celsius. Or 1 Kelvin, it's the same thing. The equation we use in here is Q equals SMAT. Q equals SMAT. It may have been MCAT freshman year. I don't remember how we did it freshman year. I think it was MCAT. But we used SMAT in AP chemistry. Whereas Q equals the energy in joules, or the heat. Energy in joules. S is my specific heat. S is my specific heat, which the units are usually in joules per grams degrees Celsius. What you would expect based on the definition. M is mass, which needs to be in grams. Watch out for conversions when you get to that. And triangle T is change in temp, also known as TF minus TI in degrees Celsius. In degrees Celsius, if your units are going to cancel out. The most important specific heat to know is water. Anybody know what it is?
8 point something.
4.184 joules over grams degrees Celsius. That is water's specific heat. 4.184 joules per gram degrees Celsius. Is that on the card?
Yeah.
Yes.
Did you get, I just have to say, Molly, you took your test, right?
Yeah.
How did you guys miss standard conditions? Yeah, a lot of people did. Question 1 on the test. Question 1 and 2 were literally up on the yellow card.
Yeah.
Some of people put 273 Kelvin for standard conditions.
Oh, let's go. I got it right.
I'm just asking. Like, I thought 1 and 2 were like home runs out of the park.
I'm scared.
Okay.
I switched it.
Anyways.
I looked
Anyways.
up and I was like, shoot, I could.
Okay.
That's the one thing I got.
Another definition
Yeah, I fidget with it.
is heat capacity. A little bit different. It's but basically the same. So heat capacity is the heat. Oh wait, I just said that. Yeah, that's the same thing. I don't know. I already talked about that. We're good. Calorimetry. Let's skip that. Calorimetry. I'm going to give you the Heller-Webster's definition. No, I'll give you the original one. No, I'll give you mine. This is Heller's definition, so I'm going to put it in quotes. All right? Energy from here to there to determine specific heat. That is a pretty good definition of calorimetry in my own words. Energy is going from one place to another to determine specific heat. If you've ever done a calorimetry experiment, you would agree that that is correct. All right? That's what we're going to be doing tomorrow in lab. Which brings me to my first drawing of the day. I know you guys love this. Are you ready for Pictionary?
Yes.
Okay, here we go.
Oil well.
A cup.
Yes, cup. Good. Excellent.
Something.
Okay. Oh, good. Excellent. Okay. So I have a foam cup.
What phone? Missed that.
It's a foam cup,
Oh,
yeah.
I messed up.
Obviously. I have water. And what do I have here?
Air. Oh.
No.
Gravestone.
Straw.
Great stuff.
Nope.
Measuring device.
Is it sugar?
No.
That's one of the 10 commandments.
Yeah, the Oreo.
No, not 10 Commandments.
Is there another cup?
The
Nope.
gateway arch.
Nope.
Should it be really easy?
That's obviously an upside down test tube full of metal.
Oh my gosh.
right?
How did we not know?
All right? That's metal. So metal shot of some kind, so little pieces of metal. All right? And I'm going to turn that metal upside down, and guess what it's going to do to the water if the metal's hot?
Make it hotter.
The metal should heat the water, right?
Oh.
The metal should heat the water, because this is hot metal. I should put hot metal.
Yeah, it was awesome.
All right? So that's hot metal that we've heated, okay? That's going to make the water hotter, or it should. We know that negative Q lost of the metal should equal the Q gain of H2O. The energy lost from the metal should equal the energy gained by the water. So let me give you some theoretical values. We're going to talk about the mass of the metal. So let's say the mass of the metal is 28.32 grams. The initial temperature of the metal, we'll say, is 98.2 degrees Celsius. Any guesses of how I got it close to 100 degrees Celsius?
Heating it in boiling water.
Exactly. I heated this in boiling water. Abby?
Okay, I have a question just on unit wise.
Yes.
So on the problem, like before, for the, you put a lowercase q for the work in, does it matter if it's lowercase or uppercase for the heat?
For specific heat, it's uppercase Q.
Okay,
all right.
and then
For the Q, EW, it's lowercase q.
Okay, but both are still heat.
They're both just energy,
Okay.
heat.
Didn't we do a lab like this in CP Chem where we
You did a lab like this in
yeah,
CP Chem.
and we like sealed it and measured the temperature.
Yep, you got it. We'll also need the mass of H2O. So we're going to say that that is 54.29 grams. We're going to need the initial temperature of the water. So the initial temperature of the water, let's say it was 22.3 degrees Celsius. I need TF of the system. So the final temperature of the system after I dump the metal in. We're going to say that that's 23.1 degrees Celsius. We also know, what about water?
Specific heat.
SH2O is equal to 4.184 joules over grams degrees Celsius. And I want to know, what is the specific heat of the metal? This is what we're going to be doing tomorrow. This is what we're going to be doing tomorrow. So let's do one here in the notes. What is the first thing I need to find out? Q lost or Q gained? What can I find out now? I can figure out Q gained by the water right now, yes? So we're going to do Q gain of H2O, which is equal to SMAT. So Q is SMAT. So let's sub in our numbers. Q equals 4.184 joules over grams degrees Celsius times 54.29 grams times 0.8 degrees Celsius. Are you guys okay that I subtracted in my head?
Wait, hold on. No, wait. Oh, yes. Okay.
TF
Sorry,
was 23.1. TI was 22.3. This minus that.
Parentheses, it does say 1.8.
Oh, that's parentheses 0.8. Can somebody grab the door? Thank you. Get out your calculator and solve for Q. Solve for Q. Or wait for somebody else to calculate it and then write it down in your notes. Work smarter, not harder. Aubrey, did you get it?
I got 41.
How many sig digs should my answer have?
1 or 4?
Well, remember, this was subtracted. I started out with 3 sig digs, right? I don't want to base it off my subtraction. So I have 3 sig digs, I have 4 sig digs, and this is a constant. Yes?
If you had measured in Kelvin, would you have 4 sigma?
In Kelvin, yes. But in order for our units to cancel out, we're going to leave it in Celsius. Which sometimes you will see it in Kelvin, but yes, in theory. So we're going to go with 3 sig digs. So rounded to 3 sig digs, Aubrey, what do you get? 182 joules. 182 joules. Okay, are we okay with that? And I know that negative Q lost of my metal should equal Q gain of H2O, which also means negative Q should equal SMAT, or S should equal negative Q over what? M delta T. M delta T, which means S metal should equal negative 182 joules over 28.32 joules, grams, thank you, grams, times math, 23.1 minus 98.2 degrees Celsius. Do you see how the math is going to work out here? Because I have a negative on top, this is going to be a negative on the bottom, right? Mm-hmm. Negative divided by a negative should give me a positive specific heat. That's why that Q loss, negative Q loss equals Q gain is kind of cool. So now you could tell me what is the specific heat of the metal?
0.092.
That's not what I got.
Let's take a second look at this.
Okay. Negative 182 divided by 28.32 times
28.32.
yes.
0.0856.
I had 0.0856. 0.0856 joules per grams degrees Celsius is the specific heat of the metal. So that's what we're doing tomorrow in lab. So you're going to be telling me the specific heat of some unknown metals. Now, you need your book. So, open up your book to
Get ready for a smattering of
page number, let's see. 228. Page 228. You're really going to want your book. You're really going to want your book for this. If you don't have one, sit by somebody that has their book so you can see this. All right? This will not make sense if you don't have your book. Page 228. This is Hess's law. So page 228, this is Hess's law. Let me summarize Hess's law quickly for you. Number one, any chemical reaction, I like to do RxN for reaction, is not one simple step. Any chemical reaction is not one simple step. All reactions have many steps.
Is this the real chemistry?
This is kind of part of it, but not really. All right, this is just kind of fun. I just had John Gorman. I don't know if you guys remember him. John Gorman just texted me, and he's up in like his 5th level chemistry course at his school, and he's like, "Remember how you taught me Hess's law?" I'm like, "Yeah." He's like, "I just used that today." So hopefully you guys remember this. It's kind of fun. Have you done Hess's law? This might be new.
Yeah.
Okay. So I do this way different than the book. So we're just going to use the book as our problem, okay? And then you're going to see, we'll decide whose you like better. So we're on page 228, and it says diborane, B2H6, is a highly reactive boron hydrate that was once considered a possible rocket fuel for the U.S. space program. Calculate delta H for the synthesis of diborane from its elements according to the equation. So I have 2 BS plus 3 H2 gas yields B2H6 gas. Here is how I like to do one of these. I want you guys to skip a lot of area. All right? So I'd skip, in my notes I have 2, 4, 6, 8, skip 8 lines. Okay, skip 8 lines at least. And we're going to write down what we're going for down here. This is how I do it. If you guys don't like it, you can read the book and do it their way. So I'm going for 2 boron solid, 2Bs, plus 3 H2 gas yields B2H6 gas. So this is kind of like a puzzle. This is kind of like a puzzle. Do you see how they gave me 4 reactions on page 228? We are going to use every one. You really need to see this on paper. Can you see that from there?
Yeah.
Okay, I'm just making sure. I'm just making sure. Okay. We're going to use every one of those to make sure to get to this reaction. So, you guys tell me where you want to start. What do you want to get first? BH2 or B2H6? It doesn't matter.
B2H6.
Okay, I want to get B2H6 on the right. So I need to get B2H6 on the right side of the equation. I have B2H6 in what reaction?
B.
Reaction B. Okay, but the problem is B2H6 in reaction B is actually on the left. So guess what I have to do to that equation? Flip it. So my first equation I'm going to use, I'm going to put reaction B here so I know that I've used it. You don't have to do that, but I'm just going to write it in my notes. I'm going to flip B and make it B2O3 solid. The states are actually helpful here. Plus 3H2O gas yields, I'm flipping this, B2H6 gas plus 3O2 gas. And because I flipped the equation, guess what I have to do to the delta H associated with it?
Flip it.
I got to flip it. So instead of negative 2035, it is now positive 2035 kilojoules. So I flip the equation, I flip the sign. I am now going to circle my B2H6 here and my B2H6 there to know that that's done. One done. What do you want to go for next? B2O3 or 3H2O?
3H2O.
Okay, I'm sorry. I mean 3H2.
Yeah.
We're down here. Sorry.
Yeah.
You want to go for 2B or 3H2?
3H.
3H2.
Yeah.
So I need 3H2. Do we have 3H2? No, but I do have 1H2. Agreed?
Yeah.
So let's use reaction C next. So for reaction C, I have H2. I'm going to write the equation first. H2 gas plus 1/2. What? 1/2 O2 gas.
This cannot be real.
It is. Yields H2O liquid. Yields H2O liquid. But how many of these H2s do I need?
3.
3. So guess what I have to do to everything in this equation? I'm going to do a 3 here. That becomes 3H2. This becomes 3/2 O2
What?
and 3H2O. Guess what that does to the kilojoules associated with it? Times 3. So I have negative 286 kilojoules times 3. These are actually kind of fun. All right, they're actually kind of fun. Do I have my 3H2 on the left now? I have 3H2 here. I have 3H2 there.
Do you need to know what the actual, or do you leave it as times 3? Do you want the actual number?
You want negative 286 times 3.
Okay.
Because it was negative 286 to start, and it multiplied everything by 3.
Oh wait.
Let's go for 2B next. Do I have 2B anywhere?
Yes.
Reaction
A.
A. Reaction A. So here's reaction A. I have 2BS plus 3/2 O2 gas yields B2O3 solid. Do I need to manipulate this one at all?
No.
No, so I'm just going to leave its kilojoules as negative 1,273 kilojoules. That gives me 2B on the left. I'm beautiful so far, right? But here's the problem. I've got some other stuff up here. So I have B2O3 here, B2O3 here. Guess what those are going to do? Those are canceling out. I've got 3H2O here, 3H2O here. So guess what those are going to do? Those are canceling out. Oh, wait, that's wrong. That's wrong. Don't do that. That's a gas and a liquid. Those are still there. Those aren't canceling. I can't cancel those. All right? Those aren't canceled. So I have H2O gas on the left. I have H2O liquid on the left, on the right. And I also have these other O2 gases on the left. So I have 3H2O gas on the left. Is there another equation?
Yes.
Equation D.
Yay.
Equation D. I need, so I'm going to write out equation D. Well, wait, are we going to write it that way? I have H2O liquid on the left. So this is good because I'm going to need H2O liquid on the, I have H2O liquid on the right. I'm going to need to get H2O liquid on the left to cancel it out. Yes? So I'm going to write out D. I have H2O liquid going to H2O gas. But how many H2O liquids do I need to multiply out? 3. So I'm going to put a 3 here, 3 here. So that means I have 3 times what for its heat? Times 44 kilojoules. At this point, if you've done everything correctly, everything else should work out. So now I have 3H2O liquid on the left, which is going to cancel out 3H2O liquid on the right. We good with that? 3H2O gas on the right, which is going to cancel out 3H2O gas on the left. Oh, shoot, but look at this. I have 3 halves plus 3 halves. What does that equal?
3.
6 halves. 6 halves divided by 3 is?
3.
Oh, that already cancels. Boom,
Okay.
boom, boom. It's a beautiful thing.
So satisfying.
It's super satisfying.
That's
Add
nice.
up your total kilojoules to tell me what the overall reaction is. What is the overall reaction? Are you doing that on your watch?
I was just doing the quick ones because I don't want to get my calculator out.
That's so funny.
That's awesome. If you would have told me in like high school that someone could do math on their watch, I'd be like, what?
Yeah.
That doesn't make sense.
Impossible.
And there would have had to be buttons too. I'd be like, oh, it's like a calculator? Like,
No, you just touch the screen.
I know what it's
Go to the Casio calculator watch.
yeah. Buttons. Did somebody get it?
36 kilojoules.
I have 36 kilojoules.
Okay, good. I was a little worried that would end up like last
So
time.
36 kilojoules is my overall heat for the reaction.
So
That is Hess's law.
does a positive delta H mean heat was transferred into the molecule?
Positive delta H, this was an endothermic reaction. You got it.
Okay.
So this reaction took heat in.
it
So if I could
required-
somehow touch that, it would feel cold
Okay.
to me. You got it. Now, look at page 229, how they did it. All right?
What?
Why?
That's a bit much.
Why?
I already don't want to do it.
Okay?
I don't,
So,
I can't even
this is all you have to do. This is way shorter than what is happening on this page 229.
There's some redundancy in some of these calculations.
There is, okay?
We don't like redundancy.
Please do it like this. Please do it like that.
Let's chill with that.
Okay. I think we can finish this, or close. Let's keep going. That's Hess's law. There you go. I'm not going to spend a lot more time on that. Now, I will say this. When you get to the problems, sometimes it is easier to work in different numbers. So you might want to start with your original equation, and maybe you want to multiply this whole thing by 2 to start. Or maybe you want to divide this whole thing by half to start. Just remember at the end, you have to either divide or undo whatever you did to the math. So I'm just letting you guys know that sometimes this first equation, based on what you have up here, it's easier to multiply this by 2. The only thing different is you'll be working in like halves instead of eighths. So you don't have to. We'll get the same thing. It just makes your math up here easier. Head nod if that makes sense. Okay.
What do you use this for?
What do you use this for?
Yeah.
So this Hess's law is just to say, like, here's a reaction. What is the overall heat for the reaction? So this is what you use it for. You're looking at all the different steps of reaction and adding them up to see what's the overall heat for the reaction. Okay. Enthalpies of formation.
Do we need like a large amount of page for this?
Here's how much I got. I'll finish it, I think. Enthalpies of formation. Enthalpies of formation. This is defined as the energy involved in the forming, I know, mind-blowing, of a compound. The energy involved in the forming of a compound, I should say from its elements. Would that be a possessive its? IT apostrophe S? From its
It
elements.
is a possessive
It
S,
is.
yes, but you
Yes,
wouldn't put
yeah,
an
you don't put
apostrophe
apostrophe
because the
because
apostrophe
it
only
is.
goes in contractions.
Okay, thank you. From its elements. So the heat of formation is known as delta HF0. And this 0, from now on, means standard conditions.
Whoa.
So anytime you see the 0, you know it is standard conditions. And we know that standard conditions are what?
290.
1 atm and 298 Kelvin. Those are our standard conditions. So I could give you an equation like the following. I'm gonna write it out balanced to save us time. So we have 4NH3 gas plus 7O2 gas yields 4NO2 gas plus 6H2O liquid. And I could ask you, well, what is the heat formed from this reaction? What is the heat of formation for this whole reaction? Here's the equation. Delta H reaction is equal to the sum of delta HF products minus the sum of delta HF reactants. Couple things. Number one, moles matter. And number two, elemental formation. Guess what the number is for that?
Just HF. No.
If it's elemental, it is still 0. Because if it's already an elemental form, there's no heat associated with that. Same as elemental form back with our oxidation. That was a charge of 0. So if it's elemental, it is 0. So flip your book to page number, this is where it gets super exciting,
We're going back or forward?
backwards. We're in the appendices.
223, can I guess?
No, we're going to the appendixes.
My book has appendicitis. I don't think it.
No.
Tracking.
Page A22 in the back. Page A22 in the back. In the very back. You will see on page A22. It starts on page A21 actually.
That's a lot of.
We have substance and state, and then we have a delta H in kilojoules per mole, delta G, which we don't know how to do that yet, and an S. Today we're only worrying about delta H. We'll hit G, delta G, and S in March. Okay? So we will talk about this whole appendix eventually. So do you guys see appendix 4 on page A21?
Yeah.
So here's how I would do this problem. Delta H reaction equals the sum of how many moles of, it's products first, right? Products. How many moles of NO2 do I have?
4.
So I have 4 moles of NO2. This is actually not hard. Times, what is the heat of formation for NO2 gas?
Yeah. Where's that? Hey. 34.
Do you guys see 34?
Kilojoules.
Times 34 kilojoules per mole. Plus, How many moles of the other thing do I have? 6, right?
Yeah.
Plus 6 moles of H2O. And that is going to be times what? This is H2O liquid. What do you guys get for that? Yep.
No.
Yep. Negative 286 kilojoules per mole. End bracket. Minus my reactants, which is going to be 4 moles of NH3 times, what is NH3's heat of formation?
-46.
Do you guys see negative 46?
Yeah.
Wait, hold on.
I have negative 46.
Yeah.
Negative 46 kilojoules per mole. Do I have to worry about O2?
Yes.
No, because it is
Elemental.
elemental form.
That's what that means.
It's elemental form. O2 is an elemental form, just like our oxidation. So, solve for your delta H reaction. It's actually not hard, just math. What do you get?
It's because it's negative.
Would you get like a sheet or would you have to?
I'll give you a sheet on the
Negative
test.
15,616.
No.
You're wrong. No. Negative 1,396.
Yeah.
1,396.
Negative 1,396 kilojoules. Negative 1,396. I can barely read that. 1,396 kilojoules. So this is going up here, just like I did here. I'm going to put it at the end of my equation. This is negative 1,396 kilojoules. I'd write that up here.
Wait, so we just figured out what we used in the puzzle?
Well, no, this is heat of formation. So this is the formation of these individual compounds. Here is the heat associated with the individual steps. Different, but it would be written the same way. Put the heat of formation at the end of the equation.
Okay.
What if I said this? How much energy is released when 10.29 grams of, it just adds, all right? It just keeps adding, of NH3 react. How much energy is released when 10.29 grams of NH3 react? What would be my first step?
I don't even know at this
The
point.
mole is always the goal. So I'm going to start out with my 10.29 grams of NH3. Rough mass of that is what?
17.
17. It's actually 17.030 grams of NH3 in 1 mole of NH3. This next step is key. The next step is my last step. This is the amount of energy I get per 1 mole. Okay? So how many moles of NH3 do I have in the problem?
As many as
I have
this is.
4, right? Agreed? I have 4? Yes? So I have 4 mole of NH3 is to negative 1,396 kilojoules. So you have to use the moles in the problem. So whenever I say moles of something, watch out, you may need to divide by 4 or something out there.
Let's start with moles math.
Moles matter. Moles matter. So, what do you get?
Negative 210.9.
Yeah, I had negative 210.9 kilojoules. Now this isn't worded great because I said how much energy is released. Technically that'd probably be a positive. It just depends, right? The wording's kind of weird. I probably should have just said how much energy is, I don't know, produced or made. Because this is kind of a double negative, right? Because if I'm saying negative 210 is release, I'm really kind of saying the opposite.
Yeah, it's gaining.
So I probably just said how much energy is formed when it reacts. Because this is already saying that it's exothermic when you get a negative number. That's the majority of the chapter. That's the majority of the chapter right there. There's a lot you can do with just that. There's a lot you can do with just that. It just keeps building.
Can you put the questions on Classroom?
I will put the questions on Classroom. I'll put it on right now, and then I'll get it written on the board. I can get on Classroom a lot faster.
Yeah.